The topic of this session is p-value and confidence interval. I will provide the definitions and discussions of these two statistical concepts. My goal is to help you understand p-value and confidence interval. I will not get into technical details on how to compute them. We will focus on the appropriate use and interpretation of the two statistics. To study a population of our interest, we often take samples from the population and make measurements on the subset of the population. P-value and confidence interval are two statistical tools to help make inference and draw conclusions about the population using the samples. P-value is used in hypothesis testing to evaluate the evidence against a null hypothesis. P-value is a numerical tool to measure how likely the effect is observed in our data if the null hypothesis is true. It is defined informally as the probability under a null hypothesis that a summary of the data would be equal to or more extreme than the observed value from the sample. P-value is one approach to measure how compatible the observed data are with the null hypothesis. A small p-value indicates it is unlikely to observe the data that is as or more extreme than this study if the null hypothesis is true. It suggests that the observed data are not very close to what the null hypothesis predicted they should be. Therefore, a very small p-value provides evidence against the null hypothesis. Next, I'll use an example of hypothesis testing to illustrate what p-value is. Suppose we study the performance of a new imaging test. We want to determine whether a hypothesis about the sensitivity of the test is true. We choose between two hypotheses. The null hypothesis is that sensitivity of the test is less or equal to 80%. It represents no difference from the current standard test, or is an effect size that we're not interested in. The alternative hypothesis is that the test has greater than 80% sensitivity. The alternative is the effect of interest, and it is what we hope to be able to conclude. A quantity called test statistic is used to summarize the distance between the data and the hypothesis. We compute its value based on the data we observed in the experiment under the null hypothesis. The p-value of the test is the chance of observing a result at least this extreme if the null is true. P-value indicates how consistent the data are with what would arise from the null hypothesis, that the sensitivity is equal to or smaller than 80%. This is a graphical illustration of the p-value. The curve is the distribution of the test statistic. In the analysis of our experiment, we calculate the test statistic from the observed data. It turns out to be the value where the red arrow points to. P-value is the probability of getting this value or the values even more extreme when the null hypothesis is true. For a one-sided test, like the one in our example, this corresponds to the shaded area to the right of the observed data. For a two-sided test, the p-value includes areas on both the left tail and right tail of the curve. The smaller the p-value, the stronger the evidence is against the null hypothesis. Since p-value is calculated assuming the null hypothesis is true, small p-values are unlikely if the data is consistent with the null hypothesis. We reject the null hypothesis and declare the result to be statistically significant if the p-value falls below a cutoff, and non-significant if it is above the cutoff. We term this p-value cutoff significance level or alpha level. The significance level is often set to be 0.05. The null hypothesis is rejected if p-value is equal to or smaller than 0.05. Do not confuse p-value cutoff or significance value with the p-value itself. Significance level is defined as the probability of rejecting the null hypothesis when the null is true. It is the same as the type 1 error. Significance level or p-value cutoff is pre-specified and fixed before the experiment. Thus, it is part of the study design. It does not change with the data, whereas p-value is computed from the observed data. This is the same figure where we show the p-value. Recall that p-value is the probability of test statistic getting at least as large as the observed value from the data, which is the area to the right of the observed data shaded in blue color. Significance level is the area in red color, with which the area under the distribution curve equals to alpha, or usually 0.05 if we set significance level at 0.05. In this example, p-value is smaller than alpha, so we reject the null in favor of the alternative hypothesis. We conclude the result is statistically significant. If the observed test statistic is on the left-hand side of the area, of the red area, where p-value is larger than alpha, the result is not statistically significant. We cannot reject the null hypothesis, or the data do not provide proof the alternative hypothesis is true. So next, I will discuss the most common misinterpretations of p-value. It may be helpful when you try to interpret the results of your own study or evaluate the reports of other studies published by other people. The first misconcept is that the p-value represents the probability that the null hypothesis is true. For example, we tested the hypothesis that the means of two groups are the same. If the test gave a p-value 0.02, the null hypothesis has 2% chance of being true. There are 2% chance that the two groups' means are equal. If the p-value is 0.8, the null hypothesis has 8% chance of being true. This statement is wrong because p-value is calculated assuming the null hypothesis is true. It cannot be the probability that the null is wrong at the same time. P-value does not say anything about the probability of the null hypothesis. It indicates the degree to which the observed data is compatible to the null. P-value of 0.02 means 2% probability of getting the result equal to or more extreme than the observed effect when the null is true. It suggests that the observed data are not very close to what the null hypothesis predicted they should be, while p-value equal to 0.8 indicate that the data are close to what the null predicted. The second misconception is if we reject the null hypothesis when p-value is 0.02, the chance that it is a false positive finding or a type 1 error is 2%. If we reject the null, the chance that it is a mistake is 100% if the null is indeed true, or the chance of false positive is 0 if the null is in fact not true. So this is another version of the previous misinterpretation of p-value. 2% chance of a false rejection of the null is equivalent to saying that there is 2% chance that the null is true. P-value is not the probability that null is true. Another similar version of the misinterpretation is like this. If we reject the null because p-value equal to 0.02, there is 5% chance that it is a type 1 error or a false positive finding when we use a test at 0.05 significance level. 5% type 1 error rate of a test refers to how often it is false rejection of the null over the many hypothesis testings we perform in our life. So it is not about the test of a single study. Also, if we reject a null in a particular study, the probability of it being a type 1 error is either 1 or 0. P-value greater than 0.05 does not imply null hypothesis is true. A non-significant difference merely means that a null effect is statistically consistent with the observed results. Non-significant results indicate that the observed data do not prove null hypothesis wrong, but the same data may also be compatible with many other hypotheses, so it does not prove the null hypothesis is true. For example, absence of a significant difference does not mean equality between groups. P-value may not be significant for many other reasons. For example, the study does not have enough power to detect the difference. The effect best supported by the data from a given experiment is always the observed effect, regardless of its significance. P-value is not a measure of the importance of a result. Statistical significance is not equivalent to scientific significance. Any result, no matter how tiny it is, can produce a small p-value if the sample size or measurement precision is high enough. And large effects may produce large p-values if the sample size is small or there are large variabilities in the measurement. Similarly, identical estimated effects will have different p-values if the precision of the estimates differ. On the other hand, different observed effects may give the same p-value. A significant result based on p-value may not be clinically relevant if the difference is too small to be important. In summary, scientific conclusions or treatment decisions should not be based solely on whether a p-value is significant. It is important to consider many related factors when we make scientific conclusions, including study design, the quality of the measurements, and validity of the analysis methods, as well as the external evidence from previous studies. So p-value is a tool for hypothesis testing, and we have seen that it provides limited information. Confidence interval is a complement that focuses on estimate of the effect. We rely on the samples from the population to make conclusions about the population. There are variations due to sampling, as different samples of the same population will give different results. When we summarize the information from a sample, we need to report the effect size and the associated variability. Confidence interval is a tool to do that. Confidence interval is an estimated range of values that is likely to include the unknown parameter of the population that we are interested in. Point estimate is the best guess of the population parameter, and confidence interval provides more information than point estimate. By presenting a plausible range of effect sizes derived from the data, it shows uncertainty associated with the estimate. A simple way to construct a confidence interval involves three pieces. A desired confidence level, we often set it to be 95%. A confidence level is the proportion of confidence intervals that contain the true value of their corresponding parameter. In other words, if we calculate, say, 95% confidence interval repeatedly in many experiments, the frequency of those intervals that contain the true value of the parameter will be 95%. The second piece is the point estimate based on the data. And then we need a standard error of the point estimate. So this is a formula of confidence interval for the sensitivity of an imaging test. For example, a 95% confidence interval is computed as the point estimate of the sensitivity plus or minus the standard error of the estimate times critical value 1.96, which corresponds to the 97.5th percentile of the standard normal distribution. The value on the left-hand side is the lower bound of the confidence interval, and the right-hand side is the upper bound. The point estimate is the best guess of the population parameter. The width of a confidence interval represents the precision with which the population parameter is estimated. The narrower the confidence interval, the more precise the estimate is on the parameter. Three factors affect the width of the confidence interval, or the precision of the estimate. The higher the confidence level, the wider the confidence. 95% confidence interval is wider than 90% confidence interval, while all other conditions are fixed. The width of confidence interval depends on the variation in the population of interest. More variabilities leads to wider confidence interval. Sample size also affects the precision. The width of confidence interval decreases with larger sample size. We often report 95% confidence interval. It means, were we to repeat the experiment many times, 95% of all 95% confidence intervals will include the true parameter of the population, or the true effect size, if the assumptions underlying the method to construct confidence interval are correct. For example, a 95% confidence interval of the difference between two groups is from -3 to 5. It can be expressed as we are 95% confident that the true group difference is between -5 and 5. With the procedure we use to generate 95% confidence intervals in repeated experiments, some intervals do and some do not include the true difference. On average, 95% times those intervals contain the true value. We know there is 95% chance that we have an interval that covers the true difference. So it is plausible that the true population value lies within the interval -3 to 5. Next, I will show a few correct interpretations of the confidence interval as well as incorrect ones. 95% confidence interval means there is a 95% chance that the calculated confidence interval from some future experiment contains the true value of the population parameter. It is very similar to the repeated experiments interpretation. It considers the probability associated with a confidence interval before we start the experiment. We know that 95% of the 95% confidence intervals we will compute cover the true effect size. A 95% confidence interval does not mean that there is a 95% probability that the population parameter lies within the given estimated interval. It also does not mean a 95% probability that the calculated interval covers the unknown parameter. For example, we report 95% confidence interval of the difference is -3 to 5. The interval -3 to 5 either does or does not include the true value. The probability of this interval covering the true value is 100% if it does and 0 if it does not. 95% confidence is a confidence that in the long run, 95% of the confidence intervals will contain the population mean. It is the confidence in the estimation procedure, but not a probability statement on an interval estimated from a specific study. A particular 95% confidence interval calculated from an experiment does not mean that there is a 95% probability that an estimate of this parameter from future studies will fall within this interval. 95% is the probability with which future confidence interval will cover the true value, but not the chance that the reported confidence interval will include future estimate. Also, a particular confidence interval either does or does not contain the true value. The 95% refers to the frequency of 90% confidence intervals estimated from many studies would include the true value. Confidence interval is related to p-value. So if a corresponding hypothesis test is performed, the confidence interval is the complement of the significance level. A 95% confidence interval reflects a significance level of 0.05. For instance, a 95% confidence intervals of an effect not containing 0 imply that there is a statistically significant difference between the two groups. If we were to perform a hypothesis test to compare two means using significance cutoff 0.05 for p-value or a 0.05 significance level. Okay, this is all I'm going to talk about today. Here I list 3 references about the p-value and confidence intervals for you to read if you're interested in this topic. Thank you.